In this video, we solved problem 97 from section 5.2 of the Larson Calculus text, 10th edition. The problem statement says a population of bacteria P is changing at a rate given by dp dt equals this 3,000 divided by the quantity 1 plus 0.25 t, where t is measured in days. The initial population is 1,000. We're asked to find P of t and then find the population when t equals 3 days. So this is just a simple initial value problem. We've got a differential equation, we have an initial condition, and we're trying to find P of t. And one of the things I want to do is simplify algebraically. I'd rather have a 1 in front of that t instead of that 0.25. So I'm going to multiply the numerator and denominator of this expression by 4 to simplify. That will give me that 12,000 divided by 4 plus t as my dp dt. That's my simplified differential equation. And my initial condition is that it says initial population is 1,000. That means at time t equals 0, so at 0 days, there are 1,000 bacteria. Okay, so you're trying to find P and you have the derivative. Well, how do you find T if you know the derivative? You just take the antiderivative of the derivative to get the original function back. So we'll do that. The derivative of P of t is this 12,000 divided by 4 plus t. You say, do I have a rule for that? No, not in its current form, but if I let u equal the denominator, I think we do have a rule for that. So we'll let u equal 4 plus t. We'll compute the derivative of u, which is 1 with respect to t. So du is 1 times dt. And then we rewrite the integral entirely in terms of u. So we're going to have 12,000 in the numerator. And that 4 plus t is replaced by a u. And then du and dt are the same. So we replace the dt with a du. Now our integral is written in terms of u. And then we say, well, what's the antiderivative of 12,000 divided by u? Well, it's 12,000 times the natural log of the absolute value of u plus c. We evaluate that antiderivative, and then we back substitute. U was 4 plus t. So this is called the general solution of the differential equation. It has an arbitrary constant in it. It's not very useful as a population function, because if you give me some number of days, you say, what is the population of bacteria after 5 days? If I plug in t equals 5, I'm going to say some number plus an arbitrary constant. That's not giving me a real population. So in order to have a population without an arbitrary constant, we need some other information. And that's this information, P of 0 equals 1,000. We know that when we replace t with 0, we replace P with 1,000, we get an equation that happens to be true. With those two pieces of information, we can solve for C. And once we solve for C, we can find what's called the particular solution. That is the differential equation, or excuse me, the function P of t that has this function as its slope that passes through the point t equals 0, P equals 1,000. So we can do that by substituting t equals 0 into this function. Now we evaluate at 0. And so we get 12,000 times natural log of 4 plus c equals 1,000. So c equals 1,000 divided by, or excuse me, 1,000 minus 12,000 natural log of 4. Because we're setting those equal to each other and solving for c. Oops, I don't know why I wrote c implies. That doesn't make sense. C equals. This implies that c equals this. All right, so P of t is 12,000 natural log of the absolute value of 4 plus t plus c, which is 1,000 minus 12,000 natural log of 4. And you might want to simplify that. You can simplify that. This 12,000 natural log of 4 plus t minus the 12,000 natural log of 4, those two terms can be brought together and we can factor out that 12,000. we'll have 12,000 times the natural log of the absolute value of 4 plus t minus the natural log of 4 plus 1,000. And the log of a difference, or excuse me, the difference of two logarithms is the log of a quotient. So we're going to have the natural log of that 4 plus t divided by 4. So natural log of a minus natural log of b is natural log of a divided by b. So that's my a, that's my b, and I substitute. So I get that. And so then I have my p of t equals 12,000 times natural log of 1 plus 0.25t plus 1,000. So we still end up with that 1 plus 0.25t that we saw in the original form of this differential equation. Okay, so that is our p of t. That's the population of bacteria as a function of time. But we can evaluate this at 0, and if we evaluate this at 0, we see we get 12,000 times natural log of 1 plus 0. Natural log of 1 is 0, so we just get 1,000, which is what we wanted. At time t equals 0 days, there were 1,000 bacteria. And we can also evaluate the derivative at 0. If we plug in t equals 0 here, we see dp dt is 3,000. You might say, how do I interpret that? Well, that's the change in the population per day is 3,000. So that means at time t equals 0, we start with 1,000 bacteria, and then every day, or at least at that moment when t equals 0, the rate of change of the population per day is 3,000. So I would expect on the first day that we wouldn't have 1,000 bacteria anymore, we'd have 4,000 bacteria. So the number of bacteria is increasing, and it's increasing very fast. So we can graph these functions. We can graph this function and dp dt on Desmos.com. And then we will also use Desmos to evaluate that function at t equals 3 days. So we're just going to substitute t equals 3 here. We'll get p of 3 equals that 12,000 times natural log of 1 plus 3 times 0.25, or 1.75 plus 1,000. But I don't actually know what that is unless I use a decimal or a calculator to approximate the natural log of 1.5. So I'm going to use Desmos to do that. So here's our graph. We've got the problem statement here. I've written dp dt equals this, which is equal to this if we multiply by that 4 over 4. And I'm really only interested in the graph for t greater than or equal to 0. So I've graphed p prime, or dp dt, for t greater than or equal to 0. And it just looks like this. At time t equals 0, our derivative value is at 3,000. So our bacteria are increasing at 3,000 per day at time t equals 0. And then after solving the differential equation and using that initial condition to find the value of our constant of integration, we have our p of t is this function. And at t equals 0, we have a population of 1,000, which is consistent with our initial condition. That's what we're supposed to have if we've calculated that constant of integration correctly, and we have, so that's good. So, okay, the question asked us to find that population as a function of time, p of t, and we did. And now we can use that to find the population of bacteria at t equals 3 days. So t equals 3 days, that number is approximately 7,715. So the bacteria, there are 7,715 bacteria 3 days later when we started with 1,000 bacteria. And then that rate of change of the population was initially 3,000. And then the rate of change was continuing to decrease as t goes to infinity. As t increases, that rate of change gets larger and larger. But 3 days later, because we started with such a large rate of change, that population of bacteria is already at 7,715. So that's a lot of bacteria.